Hi. So my name is Andrew Fleck, and I'm a PhD candidate in applied mathematics at York University in Toronto, Canada. And the title of my talk is Ergodicity, Insurance, Consumption, and Ruin. And it may seem odd. What do these terms have to do with one another? Well, I should preface this by saying that in many ways, this talk is a kind of spiritual sequel to some work I presented at EE 2021 last year. And in it, I spoke about how there are dynamics which, while having well-defined growth rates, cannot alone explain the existence of insurance contracts, right? So this would be like, for example, in the Kramer-Lindbergh model. Furthermore, there are dynamics where if you consider consumption, right, so an investment consumption dynamic, there is no well-defined growth rate at all. However, in both cases, while growth is, in the kind of EE sense, cannot explain what's happening or provide insights, another time-based operational idea from actuarial science, the kind of jewel of actuarial science, can provide some insights. And that's the idea of ruin theory, the idea of ultimate ruin. And so while I think that ergodicity economics is likely describing an important and correct modeling assumption or intuition, I don't think that growth rates are really the kind of central insight. I think that the really huge thing here is that it's the consideration of an agent through time, right? And so while growth rate maximization is intuitive and it kind of captures this temporal consideration, and there's even experimental evidence to suggest humans conform to it, I don't think it's the only important way to take time into account. And indeed, I conjecture that ruin and growth, both being kind of time-based considerations, are actually very much in conversation with each other, and that trading them off of each other may be beneficial depending on which kind of wealth regime you find yourself in. So if you seriously face ruin, it may not be as consequential to maximize growth, but conversely, if you don't, maximizing growth may take primacy. So if they're in conversation with each other, and if they're both kind of time-based, right, then we should be able to see a decision theory that can unify them, right? And this was sort of the question I had posed in my previous talk, and in today, I will try and construct a more general theory that does just such a thing. So to get to, before I continue, if you would like, you can see my talk from last year on my YouTube channel. It won't be necessary for today, but if you're really interested in these topics, it may provide further motivation. So before I get into the kind of new theory, I want to look at what may be happening and a simple example that can kind of shed some light on these issues. So I'm going to be looking at the case of additive wealth in the presence of ruin. Now, I realize when I look at the program, I can't obviously see the talks ahead of time, but I believe that Carlos Raposa is supposed to be giving a talk about just this before me. So if I step on his toes too much, or if I steal too much from his talk, I apologize in advance, Carlos. Now, we'll look at additive wealth, I guess, at the start, and we'll consider just our Brownian-Most Madrid for our wealth dynamic. And orthodox EE tells us that we want to find the utility, the nu, such that we can map it into growth rates in such a way that our kind of time average growth, our G bar, will be equal to our ensemble average growth, right? So that's this term here. And in the case of additive wealth dynamics, this is very straightforward, right? We choose a linear utility, and our time average converges to mu, our ensemble average converges to mu, and G bar equals, bracket G, and everything is nice and well defined. But there's something happening though in that picture that may not be kind of a complete picture for someone actually facing this wealth dynamic, right? So for somebody who faces a linear wealth dynamic or an additive wealth dynamic, right, someone earning a salary or fixed income, qualitatively, your bank account being above or below zero will have major effects, right? It'll be very different. And so, and whereas in the picture above, you could go below and above zero to no effect whatsoever. And so what I'm going to try and do to capture this is I'm going to define a new dynamic, right? So I'm going to introduce a stopping time, right? So what I shall call the ruin time. And it's the first time that your wealth hits zero. And I'm going to stop the additive dynamic at that point. So once we hit 0, we stay at 0, which is maybe for many situations a more realistic model for people as well. And in this case, there is no EE growth rate as we defined it earlier. So if I look at, for example, the time average growth, on the case where ruin occurs, right, it will go to 0. On the case where it does not, we just recover what we had before. And for the ensemble average, the picture is more dire because it will depend greatly on the time interval we're looking at, right? So if we're near the beginning, maybe we won't have any that have hit the barrier, but much later we may have many, and this will change the value a great deal. So these values are no longer as well defined, and they're no longer equal to each other, being random. On the other hand, it's extremely easy to determine the probability of ruin in this case. So the probability of ruin is simply going to be 1 minus e to the negative alpha u, your starting capital, alpha equal to 2 mu over sigma squared. And this is going to give a survival probability, which is just an exponential utility. And I think that this is worth noting in its own right, because this is very much in line with kind of the EE project, right? We've taken a dynamic, we have an operational criteria based on considering the agent through time, right? And we have a utility that uniquely corresponds to it, right? And so we've said this kind of is very complementary, I feel, right? So whereas before we would find a linear utility and map this into a growth rate interpretation, here we have an exponential one, we're mapping it into a ruin interpretation. And so you can see, hopefully, why I think these are so complementary. And this begs the question to me, how can we cleanly integrate these into a single theory, right? How can we cleanly integrate ruin and growth into a single theory? And also, how can we do so in such a way that a large class of dynamics can be considered, right? So we can expand the class of dynamics under consideration to include, for example, the one I just presented, the stopped wealth dynamic. And this is what I'm going to attempt to do here. So to start, I think it's very useful to think about what is actually happening in the EE decision axiom. So if we consider the time average growth, we can break our longer time interval into smaller ones of size big delta t and come up with a kind of sample average, right? If we choose nu such that the d nu increments are IID, well, then we can actually take that sample average and show it's going to converge to our expectation, right? So we're going to actually be able to show that the time average converges to an ensemble average by applying the law of large numbers. So what does this mean? For arbitrary time and arbitrary interval length, right, the implications of making these increments independent and identically distributed is that they have to be independent and stationary. And so that means that nu x has to be a Levy process. So in the jump free case, that means that we have to have that our nu x is a Brownian motion with drift, where the drift is equal to the growth rate, right? So our time average or our ensemble growth rate. And indeed, this is the key idea in Peters and Adamow's 2018 paper, where they mapped growth rates to utilities, dynamics to utilities and utilities back to dynamics using this insight. My claim, though, is that this is going to be too restrictive for an arbitrary wealth dynamic, right? So we've already seen in this talk, even just a simple stopped process can break this, right? And I want to generalize this in such a way as to have weaker assumptions and in such a way as to incorporate ruin. And to do this, I'm going to consider the fact that if I take delta nu minus g delta t, I'm going to have just a Brownian motion. So, well, I'm going to have delta nu minus g delta t. Like I said, it's just a Brownian motion up to a constant. This is an interesting process, the Brownian motions, because they're the only continuous martingales that are also a Levy process, right? And it's that latter part, the Levy process part, that's doing the work in the law of large numbers when we look at the ergodic decision axiom. That's what's really allowing us to have our time averages converge to our ensemble averages. So I want to see if there's a way that we can relax the Levy part, but keep the martingale part. Often, for starters, it's a much larger class, right? And for starters, you often look at martingales when you're looking at proofs involving ruin probabilities. So it seems like it would be a natural direction to go in. The only way we could keep our EE structure, though, and to keep kind of growth rates in special cases, is if we had a kind of law of large numbers for local martingales, right? So if we relax the Levy part, we're getting rid of our classical law of large numbers. We need a new one. And indeed, we have one. There is a law of large numbers for local martingales. Now, I just want to make a quick note. I'm using local martingale and martingale interchangeably in this talk. There is a difference, but it won't be consequential in this case, right? So our law of large number for local martingales is that if we have a locally square integrable martingale, as long as the quadratic variation is well behaved, it doesn't grow quadratically, then in time, that is, quadratically in time, then on the event that the quadratic variation goes to infinity, our martingale divided by time will almost surely go to 0. And I think it's also important to note that stop local martingales are also themselves martingales. So we can use this result in both cases, and just typical dynamics and stop dynamics, right? So how would we apply this? How would we use this? So we're going to return to the additive case. And what we want to do is we want to find a nu now such that this m, which is going to be delta nu minus g delta t, which was just the Brownian motion before, is now a local martingale. So to do this, we're going to apply our Ito lemma, and we're going to set the drift equal to 0, and we're going to get an ODE. And by solving that, we can come up with a new utility. This utility is unsurprisingly more general, and it's very exciting to me because the homogeneous solution to the ODE gives us something that looks like a ruin or survival term, right? So we have that the exponential function I mentioned earlier with the same alpha. In the particular case, we get a linear utility, which would correspond to our classical kind of EE growth utility. And so we can see this exactly what we wanted popping out, right? We can see these two terms, and we can easily see how they trade off of one another. If we pick I'm picking some arbitrary constants here, we can show that it's very easy to get a situation where at in the high wealth regime, our new utility is indistinguishable from the old one, right? That we start to only worry about linear utility and in turn growth rates. But then in lower wealth regimes, we have to start heavily discounting our wealth to reflect the possibility that ruin may occur, right? And so I think in cases where the stop dynamic exists, then we can very easily see how this would be the utility we'd want to use. And we can also very easily recover the classical EE terms here as well, because by construction, that homogeneous part of the local martingale, that new term, that ruin term, will also be a local martingale in its own right. And so by construction, it will disappear when we want to look at growth rates. So if I apply the strong law of large numbers just to m of t, I can get what looks like a kind of time average growth expression and a ensemble average growth expression if I just take simple expectations, with the caveat now that we've kind of modified them to account for the fact that we may have a stopped process, and it slightly changes the expression. But the G in our martingale, that represents growth, is still very much well defined. Now, the thing is that this quantity G will be well defined regardless of ruin, but it's not clear kind of what it is, right? In the original EE case, we had a nice kind of operational growth rate idea behind what these G bar and bracket G were. I think in this case, if we look at the utility, it kind of becomes clear that Dr. Peters' insight that our growth rates are clock speeds is what's really working here. So if I look at the utility, I can see that I'm going to get G times something in terms of units of time. So G is the scale between my time and utility. And of course, the most natural choice may be G equal to mu, but it seems I do have a certain level of subjectivity in the homogeneous or ruin part. And it's not surprising to me or unintuitive if that's the case that our agent may have a kind of different clock speed or a different coupling between time and utility as well, right? And so, like I said, it's sort of the agent's unique scale between time and utility. Now, I'm not sure how to handle the idea of subjectivity in this framework because that was one of the things we were trying to avoid with the original EE project. So this is something that might require some further study, but I think that it still has at least a kind of intuitive interpretation. So we want to have some other examples other than just the additive case. And so to do that, we have to kind of know how to apply this in general. And we have our new axiom, which is, I think, very simple, right? We say, find the new that makes the following a local martingale. And for a general itto process, that means just solving this ODE. So setting our drift equal to 0. If we would apply this to multiplicative wealth, right, we get some surprising and familiar results, right? So we get a particular solution that, as before, corresponds to what we would have had in the normal EE case. So this is our growth term. This is, which in the multiplicative case is going to be log x. But we also, in the homogeneous case, get an isoelastic utility. To me, this is exciting. What's exciting and surprising about it is that this is an extremely common utility in economics, right? So aggregation results and single agent representative agent models and stuff all rely on this. It might seem strange to have a ruin term, but you have to consider that for this dynamic, often you're considering lower bounds of some kind, right? So Anthony Brito at KIT is trying to do an ergodicity economics interpretation of real options. And I think the idea of having a kind of ruin term or a lower bound term might be able to shed insight into the time value of weighting. But this is exciting because it's building bridges between kind of classical economics and EE. Finally, I want to note that that's the exact utility you would have to derive the Black-Scholes model. So again, another bridge to kind of classical finance, which I think is exciting. I mentioned that in the investment consumption case, there is no kind of orthodox EE growth rate. And so the investment consumption case is one where we have a wealth process where we're investing a fraction of our wealth in a compounding risky asset, but we need to consume at a constant rate. So we get some dynamic that's kind of complicated and looks like this. Before, we had no new at all. The ODEs that would define it had no solution. Now we do, but we get some truly bizarre and counterintuitive results. I'm only briefly going to go over. The homogeneous part gives us a CDF that we would have expected because we're going to get something that looks like a ruin term. But we get this kind of U-shaped term in the particular case. So at large wealth limits, again, recovers the log x term. But at low wealth, there's this weird thing happening. I'm not really sure how to explain it. You can get monotonic utilities if you enforce some conditions on the homogeneous part. And that minimum of the U occurs at the level where we can no longer cover our consumption. After that point, I'm not sure what it means to say that less is more. Maybe the agent wants to leave this dynamic entirely. Or when we consider risk aversion, it might make the story make more sense because it kind of explodes in that region. But I think that this is something that's going to need further study. But I'm sort of excited because it's an unexpected result, and it exists where one did not exist before. So we've kind of created results that are more general in a situation where we couldn't even start in the classical EE case. So I want to end on a note referring right back to the beginning of the talk, where I spoke about the existence of insurance contracts and how E can't always explain it. And this is known as the insurance puzzle. And my hope really with this theory, with this kind of new theory, is to kind of create a general theory that can apply universally to explain the existence of structure or contracts in the economy, right? So it's not hard to see how trading off growth and ruin can be mutually beneficial for different agents at different wealth regimes, right? And I think that we can kind of come up with a very simplified model of the entire economy if we were to take this seriously, where low wealth agents could decrease their growth rate, but trade it off against covering ruin by paying a premium to high wealth agents who will see negligible increases in ruin, but will increase their growth rate by covering the risk of the low wealth agents. So my hope is that in much that EE gives huge insights into how contracts exist and why economics may have the structure it does, I hope that by including ruin, we can expand it to also include all of insurance as well, and kind of have a unified model for capital flows in the economy. So I've taken enough of your time. Thank you very much, and thanks to the LMI for organizing. And have a good day.